Hi everybody, Marty Geyer here from your gsp295 class, and this week we're going to talk about binary trees. So now there's a lot of terminology with binary trees. What I have up here is a sample tree, and I'm going to give you the quick bang through all the terminology, and then we'll talk about some of the other ideas and important concepts behind binary trees. Bear with me, as this might be a lot of information kind of compactly, but gives you good exposure to it, and your book does a very good job of explaining this as well. So do run through that and use that as a supplement. And there's lots of information on the web, and I think there's one or two good derived videos. If you go to the video links on the hub, it might be a good supplement here. So now, binary trees, lots of terminology. Let's start with the basics. A node. So a node is commonly referred to as one of these circly things, and that's where we actually put data. So in this node here, we have data V. Now it's important to note that you might have, like with a hash table, a key separate from data. So you might use a key to place an item and then store a slightly different piece of data, like, for example, the student ID linking to a record of student information. And so you might use the key to place it in terms of when we talk about less than and greater than in a few minutes. But you actually store different data. For the purposes of what I'm going to write on the whiteboard here, the key is the data, just to make it very simple, so we're not going to try to confuse you at all. So when I'm talking about nodes and data, I'm talking about the key is used to place it. But it's important to realize this can be separate. So a node is where you store the actual data, any of these little circly things. And what we have here is just an example tree of alphabetic letters being stored as a simple example. Now the root of the tree is a little bit backwards, upside down, what you'd think of a normal biological tree outside. The root at the bottom, trunk that goes up and then branches out. Here, we flip this upside down, and the root is always this top one here. So this is the root on the top, and the branches come out from the root, like this. So these are branches. And in a binary tree, we talk about a left branch and a right branch. First of all, in a general tree and a binary tree, let's talk about the differences. A tree is really a type of graph. In fact, if you look, draw this slightly differently. So if we connect up a couple lines here, so bear with me. Now we have a graph. And we're going to talk about graphs next week, so I'm not going to go into it here, but it's important to understand that a tree is a type of graph. All it is a graph with a couple of different lines taken away from it. What's the significance of that is because that means that using a graph data type, you can actually form a tree. So they come from graphs. And a tree is a directed acyclic graph. So by directed, it means we only go down, and all these lines should be arrows. In binary trees, we only draw them as lines because it's understood that they're directed. All trees are directed. But for the purposes of instruction, I'll draw them in here. So these are all one-way connections. And that is, when you go down the tree, you can't go back up again. And that means in terms of data structures, the way you program it too, if you start at the root and you traverse down, you can't ever go back up. You need to start over if you want to go back up and down. So it's important that it's not a two-way operation, it's only a single one, which is, again, different than graphs. And acyclic means that there are no links backwards up on the tree. So once you go down the tree, there's no links that come back up again. Not just back from where you just came, but we could have, say, U pointing up to X or all the way back up to V in a graph. And that's not the case in a tree. In a tree, they are acyclic, so you cannot go back anywhere else. Links only go down from the parent. So a root is, each node that has nodes connected is called parent. I'm sorry, let me back up and finish the tree definition. So a tree is a directed acyclic graph, but it can have any number of branches. A binary tree is one that has exactly 0, 1, or 2 branches. So here, every node is connected by either 2, as in this case, 0, no leaves down here, or 1 is in this case over here, numbers of branches. That's a binary tree. If we had another link out here, another link out there, more in other places, that would be a more general tree. And you can have those, and they are useful in some situations, but binary trees seem to be extremely useful in a wide variety of things, so we're going to focus almost completely on them. I want you to understand the difference there, that there are generalized trees that can be used elsewhere. Okay, so back to the terminology. So root, branches, and we usually talk about a left branch and a right branch. So we have a left branch off of the root here and a right branch off of the root here. What else? Leaves. Leaves are single nodes at the end that are not connected to any offspring, essentially is the term, because this is taken essentially from, as you think of a genealogical tree. So a parent node has, so Q here is the parent of E and T. A parent node has children, also called leaves. Children don't have to be leaves. Children can be connected by other nodes, as in this case. So T is a child of Q, and Q is a parent of T. E is a leaf node because it doesn't have any children down there. Descendants and ancestors are just like they are in genealogy. So if you draw a genealogical tree, Q is a descendant of E. In fact, all these are descendants of E. If you think of this in terms of genealogy, if this is a great-grandparent or great-great-grandparent, everybody below this point is all descended from that person. And if you're a child of T, then you are a descendant of T. Ancestors are the reverse. So T is the ancestor of S, and V, the root node, is always the ancestor of all of the other nodes in the graph. Siblings are just, again, like genealogically. So E and T are siblings because they have the same parent. And I think those are all the basics. So there's a lot of terminology. Your book goes over it. Please ask if you have any questions, but we're going to kind of move on to some of the other areas. So two more terms that are specific to binary trees are full and complete. So a complete tree or graph, as we'll get to too, but a complete tree is one that has all the nodes going down to the level, let's see, the right way to put it is it is full down all the way to the last possible level where you have nodes, and all of those nodes are on the left-hand side, furthest as possible. So this is not full or complete because there's nothing under E, but there are other nodes down here. A full tree is one that's filled out completely to the level it's on. So this is also not full because we're missing one here and one here. So let me clarify this a little bit. Like Z there. So if we had two nodes down here, and the tree was written like this, then this would be a complete tree. Because we have everything full down to this level. Oh, I'm sorry, I'm missing one there. Now it's a complete tree. We have everything full down to this level, and then we have nodes over to here. Even though we're missing these here, or children here, it's still complete because it's full down to this level, and we have everything on the left-hand side marching along here. And a full tree is one that is just completely filled out, as its name implies. So if we have the nodes like that, this is a full and complete tree. So if it's full, it is actually complete as well, because by definition you have everything over here. So full at this level, this level, this level, and this level, and now it's a full, completely full tree. In a second, I'm going to return this example back to the way it was, so we can go through the other items. Okay, there we go. All right, what's next? So a couple of interesting attributes. First of all, we've talked about binary search trees, binary search. A binary tree in which you search is a binary search tree. And that's the ADT, the abstract data type that we're going to talk about this week, because that's the application of binary trees. Other than just naming terminology off, that's not as interesting, or in genealogy. To actually do things and traverse it is done with the binary search tree. Now, binary trees, as you know from binary search, are very, very, very fast because they split the data in half at each data access point. So this is a tree with, let me back up 1 second, give you definitions of two more things. So levels and, levels. So levels is the one I'm missing. Levels and height, I'm sorry. So the level that you're at here is the particular, I don't know how to describe it other than the level, so to repeat it, but this is the how far down the number of steps on the path, that's really what it is, down that you are. So this is level 0, this is level 1, level 2, level 3. So everything at the top on the root node is always at level 0, and then one level down, either Q and X are at level 1, all these nodes are on level 2, and all these nodes are on level 3. At every level, you split the data more, which means you can handle 2 to the n items on every level. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 to the 4, because each one of these can have one piece of data, is 4. At each level, you can hold 2 of the end items. The height, then, is the height of a particular tree is the number of levels it has. So this actually, even though it's 0 relative, there are 1, 2, 3, 4 levels. So 0 relative levels, but 4, remember we have to work around that in arrays as well. So this is a height 4 tree. Now a data point over here is that at any given height, you have 2 to the n plus 1 minus 1 total number of nodes that the tree can hold. Now this is massive, right? Because plug in some numbers here and convince yourself that this is very, very big. Even at 4, this is 2 to the 5th minus 1, which is 16 minus 1, 15 nodes, right? At 10, this is actually 1,000, over 1,000. So you can hold huge amounts of data with just single, small amounts of levels. And you can see that with this path. So you can also traverse this extremely quickly as we with binary search. So even if this was a 10-level tree, just taking 10 path of 10 nodes down means that you can traverse it in 10 nodes, which means you only have to look through 10 things when you're trying to search through 1,000 to find the answer. And that's how binary search works, as we learned earlier in the class. So it's a log of n algorithm. And in fact, all the operations, the major operations of insertion, deletion, and getting on binary search trees are all log of n operations. So it's extremely quick. And that's important because binary trees provide a searchable, organizable way to find information, unlike hash tables. Hash tables are 001, but you can't compare two things. So you can't say, give me the next biggest thing, right? You can't do that with hash tables. So you can't get what's called ranges out of them. You can't get comparative metrics out of them. Before that, we only learned lists, which is the only other way we can get information out of something, and those are O of n, right? So this is very important now that we have a log of n way to search through things. And again, this is linked with binary search that we've already learned.